So we will wait for 2 minutes and then we'll start with this session. So welcome to week 6 live session for electrical measurement and electronic instruments course. So we will be discussing some of the previous year assignment questions for this week 6, and then we'll be, as usual, we'll be going for some extra questions. Uh, so if you have any doubts or something, so you can post that in the comment section, or you can like switch on your mic also. So these are the previous year assignment questions. This may help you solving this year's assignment question. So yeah, we'll start with the first. I think this is clear. Okay. So yeah, the first question we'll start with this. So in this week, basically we learned about current transformers, potential transformers, and then we talked about flip-flops, and then then galvanometer and like measurement of change in flux with the help of galvanometer. So these were the main like chapters for this session. So based on that, we'll be solving these questions. So the first question says that while measuring a high voltage using a PT potential transformer and a MI voltmeter, so that is a moving iron voltmeter, which of the following may cause measurement error? So in this question, we'll have to first think of, okay, PT in potential transformer. This week we learned that it is having this issue of phase angle and also this issue of ratio error. So this PT, so this potential transformer will introduce these two errors because of phase angle and because of ratio also. But the question is whether if we will be measuring the voltage with this moving iron voltmeter, will there be like effect of these error on the final value of the voltage being measured? So in case of voltmeter, what happens? It does not depend on the phase of the current, the phase of current, ultimately voltage. Okay. So you studied this in week 1 or 2 when you were discussing about PMMC and MI and moving iron, all those types of instruments. So in moving iron, we have a we have a like we pass current, and because of that induce because of that magnetic field, the irons get attracted towards that, and that's why we see the deflection. So there is no role of phase in this. So phase angle, the error because of phase angle will not be there, so we will only have this ratio error, because ratio error will change the absolute values of the voltage being measured. So that's why this will be in this case, this will be the like ratio error of the potential transformer will be the main reason for like having the error in the final value of the voltage. Okay, so moving to the next question. So in this question it is saying we want to measure an AC voltage that can go up to 500 volts. Okay, we have a voltmeter of range 0 to 10 volts and internal resistance 1000 ohms. So, and we will use a suitable potential transformer to change the range of our voltmeter. So they are saying since we cannot measure this 500 volts directly with this range voltmeter, they will be using this potential transformer. So assume the potential transformer to be an ideal transformer. Okay, estimate the power that will be consumed by our potential transformer and voltmeter arrangement while measuring 500 volt voltage. So let's see first what will be the setup for this. So initially we had this one galvanometer type and this. So this is voltmeter. So this was having a range of 0 to 10 volts, and this is having resistance of 1000 ohms, but this cannot measure this 500 volt voltage. So for that, yeah, so for that what we will do, um, we will use a potential transformer. So we have this main line, this 500 volt line something, and we are connecting this potential transformer with that, and then we will step down this voltage, and then we will be using this voltmeter. Okay, which is having 10 volt range and 1000 ohm resistance, internal resistance, this thing. So so this is what 500 volts, and this is what 10 volts. So it has to step down to 10 volts because this is having maximum output, like maximum range of 10. So now estimate the power that will be consumed by a PT, potential transformer voltmeter arrangement, while measuring 500. So what will be this power being consumed by PT? So we'll have to see the internal resistance with respect to this, or I can say impedance or resistance. In this case it will be resistance. So whatever the resistor here we are seeing here, we should we should go for the primary side resistance, equivalent resistance of the secondary side of this whole configuration. So for that, so we know this simple ratio thing, V1 by V2 of a transformer is what? The ratio of the so V1 is basically this primary side, that will be 500 volts divided by 10 volts. This is equals to I2 by I1. So this we know. Okay, now using this, uh, we can say I1 is what? I1 will be I2 by 50. Okay, we can get I this. So now what will be the power? Power will be V into I, that is V1 into I1. If we say, we can either go with V1 I1, or we can go with V1 square by Z1, Z internal. Okay, or we can go with I1 square by Z internal. Basically Z internal is R, resistance of this input side, because we don't have any inductance. They are not talking about inductance in this case. So the power will be V1 I1. So we know V1 is 500. So we don't have to measure Z internal basically, but I will also let you know what is the value of Z internal. So this is 500. Then we have this I1. I1 is what? I1 is I2 by 50. And I2 will be what? I2 is the current flowing through the secondary side. So it will be 500 by 50 into this 10 voltage drop. This is 10 volt divided by 1000. Yeah. So we will get this as, if we solve, 1.1 watt. Okay, so what was the so this is the power basically which this potential transformer will be consuming, and since I talked about Z internal, so Z internal simply, or Z internal will be R internal. So this will be what? This will be simply 1000 by, I think it's the A square, ratio is A square. So we have ratio that is 1000 by uh, 50, 1000 by 50 square something. uh, yeah, so you can calculate this. Okay, so if I do, I'll just redo this. I2 into 50. Okay, yeah, so let me know if this thing is wrong or not. I forgot whether that is a square or a. Okay, but this will be the answer for the power in consumed in the power transformer, potential transformer. Okay, so this is okay. Then the next question is, estimate the equivalent resistance of our potential transformer. Okay, so they are saying equivalent resistance. So equivalent resistance simply, or yeah, we can say we can calculate with respect to like that transformer ratio also, simply V1 by I1 also we can do. So let's see if this is correct. Now this is equal to that or not. Otherwise, this is having some issue. So V1 is what? V1 we had 500. I1 was this one, I2 by 50. So this is I2 by 50. 500 into 50 divided by I2 was, we calculated this, 10 by 1000. Okay, 10 into 1000. So this will be the input resistance. So this will be 2500 kilo ohm, I think. Yeah, so this was, so basically this A is not this, sorry for this. Yeah, you can go with this formula for our input, that is 2500 kilo ohms. Okay, so if you have any doubts while I'm solving any question, then you can just interrupt me in between, or you can like put your questions in the chat window also. So this is also easy, this was easy. Then the next question is, to reduce the ratio error of current transformer, its magnetizing current should be. So if you see the phasor of that, so you saw this thing in your lecture. So this, we have the winding resistance, and this is the reactance part of that coil, primary side coil. So because of this, we have this magnetizing current. So what happens, so let's say this was IW, that is the winding resistance current, and this was I magnetizing current, this one. So this obviously will be 90-degree phase apart, because this is a inductor, and that then the 90, so this will be 90-degree in lag with this the winding resistance. And we have this primary side voltage here. Okay, so since if we have some value of this, then what will happen, this I naught will be, so the resultant current I naught will be there. And we know this ratio error that we talked about, that is like why it is being introduced, because we saw that the primary current is IES by this, the turn ratio plus the I naught. So because of this value, we are not getting the actual ratio error, which should be there. So because of this, there is an error in that ratio. So if we can neglect this, or we can not neglect, we can reduce this I naught parameter, then we can reduce the ratio error also. So how we can do that? So they are talking about the magnetizing current. So if we can make it very low in nature, so if this will be almost zero, then this will become there, then this phasor I naught will come like this I naught. Okay, or or we can say its I naught value will reduce, the mod of the magnitude of I naught will reduce. Because of that, we can reduce the ratio error also. So for this, we should keep the magnetizing current as low as possible. Okay, so this is also fine. Then the next question, the primary side of potential transformer is connected to a, okay, high voltage line. So we have this potential transformer. So it is connected to this high voltage line. Okay, this is high voltage line, and then the secondary side is connected to a voltmeter. Okay, we want to change the voltmeter on the secondary side while the primary side is still live. So this is okay, this is being connected, this we are not like touching also, and we are talking about this side of that transformer, that is secondary side of this potential transformer. And they are saying they have to change the voltmeter, so they have to change this voltmeter and like introduce new one or like remove that. So primary side voltage is still on, select the correct ways of doing this. Okay, so the first option says that remove the old voltmeter first. So this is the voltmeter which we can look here, and then connect the new voltmeter to the secondary side of the PT. Now before going to the options, we should keep this in mind. In case of potential transformer, the secondary side should never be open circuited. Open circuit, short circuit, sorry. It should never be, sorry, it should not never be short circuited. Why? So what happens if we will short circuit this? So potential transformers do what? Like so high voltage to it transfer it to low voltage side. Like from it is a step down voltage thing, voltage transformer. So what is happening? The current is being step up. So the secondary side current is high. So IS is very high as compared to IP, that is the primary current. So if we will short circuit the output side of this potential transformer, then what will happen? Already the secondary side current was very high, and because of short circuit will become much higher. That will result in what? The in the primary side, because of this, the voltage that was already high, that will become more like higher, so it will create issues in our main line. So like lots of things can happen, like it can damage lines, or it can have like do the insulation failure or something in this side also, because of high current. Insulation failure at the secondary side can also happen, and it can damage the instruments which were being attached to the secondary side of the potential transformer. So this we should never do. So but if it is open circuited, then we have the secondary current as zero, almost zero, and then it will not affect that high voltage side. So it's fine if we are going for open circuit. So now we will go to the options. So the first option is saying remove the old voltmeter first, and then connect the new voltmeter to the secondary side of the potential transformer. So I think this is fine, because if you are removing this voltmeter and introducing something, so momentarily we are like there is a phase where we have open circuited this phase, this secondary side of this potential transformer, and I think that is fine, as I mentioned earlier just now. So this is fine, and connect the new voltmeter. This is fine. Second option says that connect the new voltmeter in parallel to the old voltmeter first, and then remove the old meter. So in this case also, like so what they are doing, so there was this v old, so they didn't remove this initially, then they added one more voltmeter in parallel to so this is new one, and then they removed this. So in this case also I think nothing will happen, because we are not short circuiting this side of the secondary side of the potential transformer. So I think this also we can do. So this both are like fine in doing in case of potential transformers. But what if this was the case of current transformers? So we in current transformers we cannot open circuit the secondary side of this of the transformer. So in that case, the first option would not have been valid if this was the case of the current transformers. Okay, because in this they are open circuiting the secondary side of this transformer. Okay, so this you have so this was mentioned in the lectures also. Now the next question. So now we also talked about flip-flops in this week. So this question says that so this is a SR flip-flop. So these are not mentioned what are these 1 and 2, S or R. So we have to say whether the terminal 1 is the set or terminal 2 is the reset input. So we'll see. So how we will approach. So let's say this is 1, this is 2, this was Q, this was Q bar. So let's say initially Q was 0. Just for the, let's assume it was 0. So if we give 1 0 in this case, so this is our table. So let's say we gave 1 at this side and 2 at 0 side. So this is what? This is NOR gate. Okay. Yeah. So this is an OR gate. So what is happening? So we have 0 here. So 0 is here. So 0 will come here. 2 is 0 already. So 0. So this NOR gate, what it does. So I'll just, this is the NOR. This NOR means not OR. Okay. That means what is OR? OR is, we have two inputs, A plus B. This is the, or this is the output of an OR gate. And if you are taking not of that, so that is like whatever there is the output, that we will take the complementary of that. That is not, or that is not. Okay. So you should, so we should know about this. So keeping this thing in mind, so we had this, let's say this, the initial condition of q was 0, we gave 0 here, and 2 was 0 already. So this 0 plus 0, it will be 0, but since this is not, so it will be 1. Okay, so this will become 1. So this 1 will go here, and we already have 1 here. So this is 1 plus 1, it will be 1 only. And since this is a NOT gate, so this will be NOR gate, so this will be 0. Okay, so we got 0 as our q value, so this becomes 0 only, so it remains 0. What if you would have given this state to our inputs 1 and 2? Then in that case, so initially now it is 0, we are like starting from this stage only. So we have 0 here, so 0 went, now the next stage is 0, let's say. Okay, or I will write in blue color. So this is 0. And this its stage is now 2, stage was 1 now. This is 1 now. Okay, so 1 plus 0, it will be 1, but we have an OR gate, so it will be ultimately 0. So we get 0 here, q bar. So this will become 0. Now this 0 will go here, and this 1 was 0 here, which we took 0. So this is 0. So 0 plus 0, it will be 0, but it is an OR gate, then it will be 1 here. So this will become 1. So what we observe when we give 1, when we set the 1 output as 1 high level, then our in the and the ultimate output, it becomes 0. And when we set second as 1 output high level, then our output becomes 1. So that means this is the set value, because this is setting this q, and this is what reset value. Okay, because it's making this q 0. So if you see the options, the terminal 1 is the set input, no, terminal 1 is the reset, and this is the second 2 is the set input for this. Okay, so this will be the answer. Okay, just see what I did here. It was like easy only, just we have to do this basic digital, apply digital concepts only in this case. So now if this is fine, we'll move towards the next question. So how many flip-flops are required to generate a 5 kHz square waveform from a 160 kHz clock using a binary ripple counter? So this you have done in this week also, so it's like direct formula you can apply. So this basically log 165, this is base 2, so it will give 5. So this is the mod value of this thing. Okay, otherwise there is a full proper derivation also, like for n mod, how you will derive this thing, so for t flip-flops, but if you know this, then it's fine. So I think this is also okay. Then the next question is, again we have a current transformer question. So they are saying, oh okay, we discussed this, but okay, the primary side of a CT is connected to a high ampere line, okay, and the secondary side is connected to an emitter. Fine, so we have this current transformer again. The secondary side is connected to the emitter, that is we have this emitter, and this is like the main, the primary line. So, and this is very high value of current, this primary side IP, this let's say IS. IP is very greater than IS. So select the correct ways of doing this. So we have to change the something on secondary. So what we are doing here, so let's see the options. So connect the new emitter in parallel to the so in CT, what I told you, in case of CT, we should never open circuit this, the secondary side of the CT, that you have learned in lectures also. So what will happen in this case, we have to connect the new emitter in parallel to the old emitter first, and then remove the old emitter. So yeah, in this case we are avoiding this open circuit situation, so this is fine. Second is remove the old emitter first and then connect the new emitter. So we cannot do this because in this case there is a chance of open circuit, because we are first removing the old emitter and then we are using the new one. So this is, B will not be the option for this. So A will be the option answer for this. So this is also fine. Then we have this ballistic galvanometer type question. So this was being discussed in the lectures. Like we have N1 and N2 turns of this circular core transformer, and we have this ballistic galvanometer, and this will give us the change in flux density. So for this, like so we know that EMF is what it is, N d phi by dt. Okay, or we can say and change in delta and change in flux. And what is change in flux? So change in flux will be basically B into A into delta t in time. So this is B, because B is like the change will be only when we are like when this is being removed. So whatever the magnetic flux was there already, that will only become zero after opening this thing. So whatever B was there before the opening of the switch, that will be the final change. So basically delta B will be B itself. B is like old value of the magnetic flux. Okay, so we have BA here, and EMF is what? So EMF is like I2, the current I2. Okay, I2 into R2. So we have this. So and I2 will be what? dq by dt, they change the rate of flow of current, that is. So dq by delta t, this is R2, and BA by delta t, this delta t will cancel out. So delta change in q, we can get this from the sensitivity of this thing, galvanometer. So how we can get? So this is microcoulomb, so S will be equal to this will be what so we will be basically multiplying the deflection, we know. So multiplying deflection by the reciprocal of the sensitivity, we will get the microcoulomb, and the microcoulomb value was, it was 2.85 microcoulomb. It came out to be 2.85 microcoulomb. Okay, so this was the like the flow of this charges. So we have this. So ultimately we had to calculate B. So B will be Q, that is this Q into R, that is R2 divided by A into N2. So this formula only we used here. So Q we know, R we know, this is 4000. Area of cross section we know, 1 centimeter square. So don't just remember to change the units of that in that metric unit, standard units. So then we have this N2 tons will be 500. So we can get the density of this B, the flux density in the core before the switch was opened. So I think this is just the application of what we studied in lectures, and you know the formula also. So I just told that same thing. And then the permeability of the core. So permeability can be, so we have this mu H equals to B. So we know B, we need to calculate mu. So mu will be B by H, and H is the intensity, the magnetic field intensity, that is basically Ni by L. So it is H is given by N1 I1 by L. Okay, so basically the current, the total current, that is N1 I1 divided by the length of that path, that will be the magnetic field intensity. So this will give you yeah, so based on this you can calculate the permeability also. Okay, so this is also fine, this is also fine. Then we have another flip-flop question. So in this case, we are talking about D flip-flop. So for D flip-flop, so they are saying the above figure is of positive edge, negative edge, level trigger D flip-flop. So positive edge, like when there is like clock pulse is getting high, or negative edge is like when it is moving towards the lower level, and level triggered D flip flop is when it is at this position at its high state. So let's see what will happen. So if we gave one input here, so this will make this is an OR gate. So you know this, I think this is an OR gate. This will make this 0. So this will be 0. This will be disabled, but this will be 1 again. So because this 0 came here, and then it will make this 1. So this will be 1 enable. Okay, I will start with some with zero input. Then you will understand this more. So let's say we gave 0. Okay, initially clock was 0. Then let's say clock was like this. So this became 1. This was enabled. So whatever value was there, this holded that value and it was presented here. So let's say some value came, some q value came, q. Okay, so this came q1. Let's say this is q1. It came, so it is holding that, and this will be 0 because we gave 1 here, and then this enable was what, this was 0, so this was not active. Then the clock became high, so this was there, then clock became high. So but ultimately what is this value, q value? So because we are talking about this whole thing in total, so we have to see when finally we are getting this q output. So Q output will be given only when, if we change this 0 to 1, then what will happen? This will become 0, this will be disabled, this will be 1 then, and this will be enabled, and finally we will get the output. So what happened when it was becoming high, that is positive edge, then finally we got the output for this thing. So this will be the case for positive edge triggered. Okay, then the next question is of CT. Okay, we want to measure an AC current that can go up to 500 amperes. We have an emitter range of, okay, we have this range, and internal resistance of 10 ohm. Let's draw the diagram for this, uh, like this, and we have an emitter here, and it's 5 ampere range and 10 ohm internal resistance. We will use a suitable CT to change the range. So this is CT which we used here, and this was the main line, that was 500 ampere, sorry. So this was 500 ampere, and then we have this, assume the CT to be an ideal transformer, estimate the power what will be consumed by our CT and emitter arrangement while measuring 500 ampere current. So they are saying what will be the power being used by CT. So again we did something similar to, I think, P with respect to PT. Initially we had to with respect to PT we did the calculation of the power. So in this case again what we can do, so this is 5 ampere. So this power can be V1 I1. So what will be the voltage for this side? So this will be we know V1 by V2 equals to the ratio, so that will be I2 by I1. So I2 we know that is 5 ampere, I1 we know that is 500, so we know this. So V1 will be what? So V1 will be 5 by 500 into V2. Okay, and also I2 is, so do we have the value for this? Okay, and what is V2? So V2 will be 5 by 500. So V2 is this thing, the secondary side voltage, that will be like 5 ampere is the current flowing, and we have the resistance 10 ohms, that will be into 5 into 10, simple Ohm's law. Okay, So we will get V1 value from here. I1 we know 500. So power will be this thing V1 and I1 here. Okay. So this is the total power. So you can calculate this. This is easy then. Then if this is fine, so this is like similarly what we did in PT, potential transformer. So now the next question: estimate the equivalent resistance and of our CT and ammeter arrangement as seen from the primary circuit. So they are asking that same thing. This will be V1 by I1. You can easily calculate because you know V1, you know I1, so you can calculate V1 by I1. Okay. So this is also easy. Okay, fine. So now we are done with the assignment questions. If you have any doubts in this, uh, so based on this, you can now I think solve the this week's assignments. You still have 1 day left for that solving the assignments. So I hope you will not find any difficulties solving those assignments. So this was for the assignments for mm, solving those. So now we will move towards some extra questions which will help you in like for the final exams of this course as well as for like some competitive exams, plus it will enhance your understanding of this course also. So this is the first question. Sorry for this example 9. Just read this and try to solve this. So just if you don't have any pen paper or something, you can come with that and try to solve that. So we'll solve one by one some questions today. So we will be having some questions on AC bridges, and then we will move towards this current transformers and potential transformers, some questions related to their errors, and then finally we will move towards the flip-flop questions. And gradually from next week we will be moving towards operational amplifiers, so which will be one of the interesting topics to learn. So yeah, we'll go with that. So first of all, yeah, if we focus on this question, so try to attempt this. So in this question, so the question says that if R and C are variables connected as shown in the vein bridge, so we have this vein bridge, so this is the configuration for a vein bridge. Then so we have this when bridge is balanced at f equals to 1 by 2 pi c. So when you calculate equation for balance equation for vein bridge, so you will get, so for that for this frequency it will be balanced for that case. So once you solve that balance equation, you will get that. So they are saying given which of the following is true when bridge is balanced at f equals to 3. So you have to say which will be true. So again, for any AC bridges, if they are talking about this, so just focus on their balance conditions. So how the balance condition will look like in this case. So it will be I will write down this for you. Just correct me if I'm wrong. So this is the like so deflection is here, like you can say this is the deflection or this thing. Okay, not to draw it again. So this will be R4 into R plus 1 by j omega c, or we can say or just for the simplicity, this will be R4 by R3, these two R3 R4 by R3 equals to this parallel combination of this, that will be R1 by j omega c, R plus 1 by j omega c into the series combination of this R plus 1 by j omega c. So if you rearrange these things, then what will you will get this r4 r plus 1 by j omega c equals to r3. I'm going there, I'm bringing that there, and this will be r1 by j omega c r plus 1 by j omega c. So I think now it's like just you have to see, just you have to then equate the real and imaginary parts after solving a little bit more. So we will get some equation like, so if we equate the imaginary part of this, or I will just write the full equation for you. So this will be c square omega square uh, r square plus 1 plus 2 j omega rc, which equals to j r3 r c. So you can like check on your own also whether this was correct or not, but I think this is fine. So if we now after, so this was after solving this. So now equating this thing, the real and imaginary part of this equation, we will get rc r4 r3 rc omega. So omega will cancel and r4 will be r3 by 2. R cancel, c cancel, so r4 equals to r3 by 2. So normally AC bridges questions are like this straightforward. So you don't have to, just you have to equate the balance condition for this, for that bridge. Okay, so this is nothing. So now the next question. So we have like kind of similar, but so this we have these different uh, like conditions for the balanced state. For a balanced bridge shown below, what are the expression for r3 l3 q3? So I will write the balance equation for you, but you can get to the answer on your own. R3 plus j omega l3 into r2 by 1 plus, simple again, no issues in these question. So just use this equation to get the answer for this, and the answer for this I will tell you. So you can do this in like homework, as a homework you can do. So answer is C. So just as a practice you can do it on your own self, on yourself. Okay, if you face any difficulties, then just let me know in the next session. So this was fine, but I wanted to like make you solve this question. So this is interesting. So now this question is saying, if in the bridge circuit shown below, the sequence that is most suitable for balancing the bridges. So now this is something different, some different question based on AC bridges. So they are saying in order to find the balance condition for this bridge, then what you will be using in these four options, like will you be adjusting r1 first and then adjusting r4 to get the balance condition, or you will be adjusting r3 and then r2, or r1 and r2, or r3 and then r4. So for your simplicity, I will write down the balance condition for you. So based on that, you can use some logics and then solve that. So the balance condition for this will be r1 r4 equals to r2 r3 plus x1 square plus j x1 r2 minus x1 r3. Now think what should be the option, which option should best match the balance condition. So this is the condition when this will be balanced. So now so what you will be doing so that you can achieve this condition, what will you do to achieve above condition? And how I got to this equation, then again I saw like use that balance condition thing, or like ratio of the arms I equated, and then I got this thing. Now after this, now just think for 2 minutes, just think, and then I will tell you the answer. So for simplicity also you can approach like this R4. So you just equate the real and imaginary. So real part will be R2 R3 x1 square, and imaginary will be x1 R2 equals to x1 R3, because there is no imaginary here. So this x1 will get cancelled. This is R2 equals to R3. We have one equation for this. So let's go one by one. So what, let's see the first option. So what it is saying, so it is saying that first adjust R1. So they're saying adjusting R1, that means they are like you doing something in this. So they adjusted R1. Okay, they got to some value, and then they adjusted R4. But we cannot say anything about these R2 R3 or x1 in this case. Although we can adjust this, or we can say for the balance condition the real and imaginary part should be equal for this side and this side. So although we adjusted this R1 and then we adjusted R4, but we didn't talk about anything about the imaginary part of this equation. So how we will be able to balance the imaginary part of the equation? So we won't get the balance condition for the imaginary part. So that's why we cannot do this. Okay, let's see the third option again, because it is adjusting R1. So let's say we first adjusted again R1, and then it is saying we adjusted R2. So although first we adjusted R1, then we are adjusting R2 for this case. So can this be the answer? Then again, what if this R2, what we adjusted according to this equation, if it's not fitting this equation, that means that what we adjusted R2, it is not equal to R3, like that. R3 was not equal to R2. Then again we won't be able to achieve the imaginary part balance condition. Getting? Now let's see the answer itself, the most valid answer what we can get. If we adjust, let's say R3, if we adjust R3, we adjusted R3, we made this some value which we made this R3 equal to R2. So R3 R2 are equal now. Okay, so we achieved the imaginary balance condition for this equation. After that, now we are moving towards the real part, balancing the real part of the equation. In these scenario, what was happening in first and A and C part, they were first adjusting the real part, but then imaginary part adjustment was having issues. So in this D part, what we are doing first, let's say we adjust this R3, and then we adjust R4. So R3 equals to R2, we adjusted that, so we don't have to care about this. So now we have to adjust just these, so now it will become R1 R4 equals to, so this is some constant plus x1 square. So if you only then adjust R4 after this, then somehow we can achieve this value. What if we talk about this B part? So we didn't discuss this. So they are saying first adjust R3 and then adjust R2. So if we already adjust R3 and then we again are adjusting R2, then only we are focusing on this. So why to do that if in the fourth option we can adjust three parameters with two adjustments? So first we are adjusting R3, because of that we got R2 equals to R2 equals to R3, and after that we adjusted R4 in the real part equation, so that we can achieve the real part imaginary condition, real part balance condition also. Okay, got my point? I hope I am able to make you give the clarity on this question. So we adjusted R3 first, so that we got R2. So we adjusted R3 means we made that R3 equal to R2. So we achieved the imaginary balance condition. After that we went for the real part, and then we adjusted another parameter, that is R4, so that we can finally get the balance condition for the real part of that. So this seems more approachable uh, option for balancing this bridge. So and so this is completely based on what type of balance equation you are getting, and what and based on the logic which you are applying in these kind of questions. Okay, so there may be some other type of bridge where you have to adjust some other parameters in order to achieve the final balance condition. So just think of, like, with minimum adjustments, how you can achieve the maximum, how you can get the maximum results. So in this case, with two adjustments, you get the imaginary balance condition. You were able to like get the balance condition for the real part. So basically, you were able to adjust the three parameters or four parameters by just adjusting two parameters. So think in that manner for these type of questions. Okay. So this was for the AC bridges. Now we will move towards some questions related to PT and CT, which we are discussing this week. So yeah, the first question is easy. So in case of potential transformer, if the load on the secondary side increases, then what will happen? So this we have potential transformer. Okay, so load means basically the current on the secondary side. So there was some load, some resistance or something like that, and we had the secondary current at the it's this side, and we have IP here. So first of all, what is ratio? Ratio is directly proportional to this. So normally we have V1 Vs V primary by Vs equal to Is by Ip. So this is for the ideal transformer that we will not talk about. But normally the ratio is directly proportional to Is by Ip. Okay, the secondary current and then the primary current. So if we increase the load, that itself means we are increasing this Is value. So it will increase, like, so for a potential transformer, Is is very high than Ip, because this is a step up voltage transformer. So sorry, step down voltage transformer. So the it will be it will act as a step up current. So Is is very high. So if we are increasing the load, that means already Is was very high, so it increased a lot then. Although IP also increased, but not to that extent. So ultimately we will have some increment in the ratio error. So since this is increasing, ratio is increasing, so that means the ratio error will also increase, as we have IP equals to Is by A plus I naught something. So this is increasing, so this will result ultimately in increasing of the ratio of this ratio error of this PT. Okay, one thing. The second thing they are talking about is phase angle. So how you will comment on the phase angle of this? So what happens, like, so Is increased, that means what happened to the primary side, the Vp. So this is a step down. So already Vp in this case is what? Vp is very high than Vs. Okay, but if we increased Is, then Vp become much higher than Vs. So if the primary side voltage is increasing, that means its phase angle will also increase. Okay, so when, like, if the load on the secondary side increases, so it increases the secondary side current. That means the primary side voltage is also get increased by a very high amount, and then it means, like, it will create issues in like ratio error and as well as the phase angle also. So if you want to get more clarity, if you want, so I can derive the full, like, ratio error and the phase error equations for this. But if you want, so you can post me in the discussion forum or chat window. I can do that in the next session, but it will be little lengthy. But okay, I will give you the expression for that. uh, just for your clarity, I will give the uh, expression for the phase error and this ratio error of this potential transformer. Just wait. Ratio error, and we have phase angle error. So just wait for 1 second. So when we increase the secondary current, that is the load current, then ultimately the ratio error and the phase angle error increases. Okay. So otherwise, yeah, you don't have to remember these equations, these big equations. Okay. Now the next question. Let's see. So this is a potential transformer used to measure high voltage by using. So in this, so if the potential transformer is being used, that itself states that what it says that it is stepping down the voltage. So I think this is very easy. So for like low voltage, you only need low range voltmeter for that measurement. Okay. Now the next question. So this is an interesting question. We'll solve this. First, read this question. So the question is saying a current transformer rated 100 by 5 has magnetizing and loss components of the exciting current as 1 ampere and 0.6 ampere respectively. The secondary winding burden is purely resistive. So this means like basically the load at the secondary side of the either current transformer or the potential transformer. So what happens, like when we connect the secondary side of these potential transformers or current transformers to our circuitry, where we have to like give that voltage which has been transferred from the main transmission line, a voltage in case of potential transformer and current in case of current transformers. So we attach like different protective elements like relays. We attach like different types of relays, different type of switches and ammeters, voltmeters, in order to measure that, in order to protect our circuitry, outer main circuitry. So those all things we called as burden. That is the burden. So that is like a burden. You can literally also say it is a burden for that potential transformer. It didn't want that, but actually we will have to use that, because otherwise we won't be able to protect our measurement circuitry from any type of surges or some kind of that things which can happen. So that is like this burden thing. Okay. So now they are saying this is, let's say that it was purely resistive. Okay, we accepted that. Okay, it is purely resistive. So they are saying now what will be transformation ratio at rated current. So now observe this question. So they are talking about CT. So they have this ratings 100 by 5. So that means this was what? This is primary current. This is secondary current, because it is it is stepping down the current, the secondary side current for that. So or definitely by logic also we can say this will be the secondary side current, which should be low. Okay, so this is 100 by 5, but actually because of this magnetizing and loss components in the primary side of that current transformer, what happened, we will not get this ratio. Okay, so this will be what, this was 20, but instead of 20 we will get something else. So that is the ratio error which we have talked about in this week, and we have talked about in the previous questions also. But now what will be that value, what will be the ratio error, what will be the final transformation ratio after this introduction of magnetizing and loss components there? So just recall, you have been taught this equivalent circuit of this transformer. So we have this. Okay, we have this winding resistance, we have this magnetizing reactance xm, and we have I naught here. We have this coil winding, we have the secondary winding, and then we have something here as a load or something. So this is secondary side, primary side, and this we have input, that is line voltage or something, whatever, V1 we can say, VP you can say. Okay, and this is EP, and this we have ES. So ultimately what is happening, if we draw the phasor, so let's say IM, the magnetized, so this is IM. It's simple, it's not that difficult. It's IM, and let's say this is IW. So what, so this is EP. Let's say this was, we just drawed EP here. We are taking this as EP. So this voltage is across this whole parallel branch, that is RW and XM. So this XM IM current, so what will happen, this IM, this will lag this voltage EP by 90 degree. Why? Because the inductor current lags its voltage by 90 degree, that you know, already know, that is basics. And this winding current, what it will be, it will be in phase with this EP voltage. So we can draw this it as here IW. So this is IW here. What will be I naught? So it will be basically the resultant of IM and IW. That will be this. This will be I naught. Fine. Now this we know, this is IS by A. That is the transformation ratio. This was IS. So we have like reflected this IS here. That is just that thing. And this was our IP, the primary current. So now how transformation ratio error will occur? So now it will be so now IP will be what? IS by A plus I naught, that you already read in this lectures, in these week lectures. Now what will be the ratio? Ratio will be IS by A plus I naught divided by what? IS. So because of this, there will be issue of this ratio, and this is what? This is 1 by A. I'm just denoting that IS by. Okay. So because of this I naught, there will be this ratio error, and that what we have calculated. What we have to calculate. So if I naught would not have been there, then we would have got this as the ratio 20. That is what being rated here. Okay. But now we will get some extra thing because of I naught. So first of all, calculate what is I naught. So I naught, you can easily calculate what will be I naught. It will be IM square plus IW square. Easy. Okay. So it will be 1 plus 0.36. We know the values, 1 ampere and 0.6 ampere for the loss component and the magnetizing component. So we will get 1.36 under root of that. So this we got. So this we know the value of this. Now so see what will happen. This will be IS by A, and this will be somewhere our result, our IP current. Okay. So we have this thing, something like this. So we need to calculate this IP. So what will be IP? So I'll add one page here. Add. Okay. Yeah. So now we need to calculate IP so that we can find the transformation ratio, new transformation ratio. That will be IP new by this. Let's say this is IP prime by IS. Okay. So this we need to calculate. So how we will calculate this? So IP. So we have two vectors. This I naught we know, value of that. IS by A we know. So and also we know this so this angle alpha, let's say the angle between this will be what? This will be okay. So one thing to keep in mind, okay, I have to tell you that first. Okay, sorry for that. Let's see the phasor again. So we forgot about this thing. So burden is purely resistive. Now I will tell you the full phasor of that, how we will do that. So this is the primary side EP, and I will simultaneously draw the resistance, so you will get the full clarity of what we are talking about. So this is some resistive burden here. IS is here. This was ES. This was EP. This was XM. This was RW. This was IW. This was IM. This was I naught. This was IS by A. This was, let's say, JXP. We have this RP. We have this as V primary voltage. We have primary current here. Okay. Now we have this thing I magnetizing current, that is lagging the main EP voltage. This the voltage at the windings EP by 90 degree, that we know. We have IW here, that is the resistive part of that will be in phase with the EP, that is clear. So then we will have a resultant I naught here. Till this we are okay. Now this ES, we will draw the phasor of ES also. So ES, according to Lenz's law, it will be in 180 degree apart from the EP, because EP induced ES. So based on Lenz's law, we see induced EMF is what? Minus N d phi by dt. Okay. And also you can say that Lenz's law opposes the cause. So that's why the phasor of this will be, ES will be this one. Fine. Easy, no issues. That is 180 degree apart from this EP, because EP induced ES. So this is because of Lenz's law. Now we have this IS. So IS will be what? Since the burden is resistive, IS will be this one, IS. Okay. So this is IS. Now if we talk about IS by A, that is the IS reflection of IS in terms of primary. What it will be? It will be somewhere here, 180 degree here. IS by, oh, it is some IS by A. Okay, this will be IS by A, because now see, the sense of the current IS was this side, it is this side, it is downward, it is upward, so that's why it is 180 degree also. So you can easily get that. So if we talk about IS by A, this vector, this IS by A, then it will be 180 degree from IS. That is easy. No issues in that. So we have IS by A here. Now what will be the resultant? So IP is what? IS by A plus I naught. So so 1 by A, we already know that is 100 by 50. This ratio we know. Just for the clarity I'm saying. So now we have resultant like this, IP. Okay. So because this is this vector plus this vector. So this, we have this vector, we have this vector. Two vectors adding, we get IP vector. So now they are saying what is IP in order to get the transformation ratio. Now I think you will get the clarity. So we need to calculate IP. So for calculating that, of magnitude of anything, I naught square, simple vector addition if I go with, then it will be IS by A square plus 2 I naught IS by A into cos of angle between this will be alpha. Let's say this whole angle is alpha, cos alpha under root. This, you know, simple vector addition. Okay. Now we have to calculate what will be alpha. We can get this value, that is theta. Theta will be what? So we know IW, we know IM. So it will be tan inverse of base upon hypotenuse, that is IW divided by IM. Simple. And IW is what? IW is 0.6, that is given in the question, and IM is 1. So this is tan inverse. So this will ultimately, this we will get as 31 degree approximate. 31 degree. So we got this as 31 degree. So we know full angle is 90. So alpha will be what? Alpha will be 90 minus 31. We got this as 59. So alpha we got as 59. Fine. So alpha we have, I naught we have, is we know, a we know, so we can calculate the magnitude of ip. So if we substitute all things here, ip, I will directly write it for you. So ip will be 100.6055. So now you will observe that if we go for the, now if we calculate the transformation ratio, it will be ip by is, that will be 100.6055 divided by what, output secondary current is 5 amperes, so this will be 20.1211. So now observe this, now you will appreciate also. Initially we had this thing, they told 100 by 5. If this transformer would not have this loss components, exciting currents and loss components and magnetizing currents, then the ratio would have been 100 by 5, that is 20. But since we had this magnetizing and loss components, because of that we we got this variation in this angle, we got variation in this ip, and that variation is this 0.6055. Because of that, what happened, the transformation ratio instead of 20, it become 20.1211. So this 0.211 is the absolute error in the ratio. So now what will be the answer? Transformation at the rated current will be 20.121. Okay. So now you can imagine or like analyze like this also, what is actually happening when we are introducing this magnetizing and loss components of the currents, what actually is helping. So I told you about this phasor. This is easy and as well as very intuitive to understand what happens in general transformers also. So when you will be learning about transformers in machines 2, I think machines 2 or machines 1, I don't know, but then also this phasor will be really useful for you. So that's why this you should know about this, and also to calculate this ratio error and all those things, so you should have this idea of this phasor. So this was this thing. So, and I told initially also about this ratio error and phase angle error thing. So here also it was like with help of this phasor only we achieved that equation for ratio error and phase angle. So if you are really interested in that, you can like derive that equation on your own also, or you can, yeah. So this was the thing for this question. So if this question is fine, then we'll move to the next question. That is simple to answer, not a like a mathematical question. So the question says the current in the primary winding of a current transformer depends on the. So they are saying current transformer. We have current transformer here. Then we have current in the primary winding. So it will depend on what. So I already told what is burden. So burden is basically whatever extra things, relays, ammeters, voltmeters we attached as to like protect our outer circuitry, and also in order to measure the voltage or current in case of CT, PT respectively. Okay, so that is burden. Burden of the secondary winding of transformer, that is one thing. Or load connected to the system in which CT is installed, or both burden of the transformer secondary winding and load connected to the system, or none of the above. So in this case, when we attach this current transformer, its primary winding, so whatever, so what will be the answer for this? So this like wordings may be confusing for you because it confused me also. So this load connected to system, this basically they mean by the main system from which they are drawing this current. That is this system. Okay. So load, you can say that it is a secondary load. Normally refers to the final secondary side load, but no, it's not. It's the main system thing. So this wordings may be confusing for you, but they are talking about the main system thing. So basically the answer for this is B, that is the current which is being drawn from the main system. So whatever the current it will, there will be, so there will be, so based on that only we will get current at the secondary side. So whatever IP we have, based on that we will get IS. So if we change load here or do something else, it will not affect the main line current, that is very huge and that is being controlled by power systems and grids, all that thing. So that will not affect this main line. So load connected to the system in which CT is installed, so that current in the primary winding will only be affected by this. So this is the current being flown from this winding, primary winding, from this side. Okay. So so burden, whatever burden we have, although it will introduce errors, but it will not affect the main system current or the primary winding uh, current. It will introduce phase angles and all, phase angle error and all those things. Yeah, but this current it will not affect. Okay. So now, yeah, next question. So this again we have magnetizing. Now I will, so by this question you will get more clarity about what we talked earlier, this the concept of this errors and all those things, and the phasor of that, that is very important. Okay, so I'll add one page and we'll go in continuation. Mhm. Yeah, landscape done. Okay. So city, yeah. So again we'll go step by step. First of all, we will draw the diagram of a phase transformer, sorry, current transformer, what I'm saying. So this is the primary voltage, or you can say the main system voltage. This is RP, this is JXP, this is RW, this is JXM, we can say. This is I naught, this is IM, this is IW. Now I think you can follow more easily what I will be telling. So this will be IS by A. Now in this question they are saying the phase angle between secondary winding induced EMF and current is 30 degree. That means initially in this question they said this the secondary winding that is purely resistive. That means there was no angle between IS and ES. But now in this case what happens? In this case the phase angle between secondary winding induced EMF and the current is 30 degree. Means there is something here which is causing this current to be there. Okay, so how we will see that thing. See, so let's say this was not the not that ideal secondary side of that current transformer. There is some inductive part also. Because of that, I think because of that only there is some angle between the secondary side current and the secondary side voltage. It will be clear for you just in a while. Just wait. So this is, let's say, ES that is being induced here, secondary side voltage. This is EP which induced ES. Okay, this is secondary side current IS. Fine. So this we had, this we have this thing. So this is the imperfections of the secondary windings. That is resistance it has and some inductance. Okay, let's see like that. And this we have, so this is this VS voltage that is basically around this these windings. Fine. So let's draw the phasor of this thing. Again, what we will do, so we have this EP. Oh, It's not straight. So we have this primary side volt EMF. We have this magnetizing current IM. This IM across this EP was there, and IW will be this IW. This is the resistive winding current that will be in phase with EP. This will be IW. This will be IM. So this was the flow of flux in this core, phi m. Okay, so this is flow in which Im will be there in phase with that flux. So this, it will be lagging this EP by 90 degree because this is purely inductive in nature. This much we just discussed. This is I naught, this is I naught. Okay, I naught, that the current, the loss current. And then let's talk about the secondary side. So this again, ES will be what, 180 degree because of Lenz's law. This will be 180 degree apart from this EP, this primary side EMF. But now they are saying the phase angle between secondary wire induced EMF, that is ES, that is the secondary winding induced EMF, and the current is 30 degree. So ES and IS are having 30 degree this lag. But earlier in that question, since the burden was fully resistive, so this IS was in phase with this ES. Okay, this much is fine. So now Vs will be what? Vs will be in this phase. Fine. Now if we just talk about IS RS, like the drop across this and the drop across this, that is IS excess J, this is 90 degree, that what makes ES. Okay, so ES is what? It is equals to IS RS, simple, like I'm doing KVL only, plus J IS axis. So you should have full knowledge of this, full understanding of like phases. So it's simple, like what is ES? ES is the resultant of drop across RS and drop across axis. So what I denoted here itself, simple, nothing I did. So this how ES was made, because of drop across RS and axis. And we have this 30 degree, we know. So now what will be IS by A? IS by A, since it on the primary side, so we will make this 180 degree backward, and this will be IS by A. Okay, so this is IS by A, 180 degree backward. So now what is IP? IP is IS by A vector plus I naught vector. So these we have two vectors here. So this will be IP. Okay, this will be IP. Till now I think it's fine. If you have doubts, you can just interrupt me. So this is okay. Okay, IP we have IS by A. We draw the full phasor. We have now overview of what the system is, what the question is saying. So we had this 30 degree. So this 30 degree will be here also. This will be 30 degree. That is the simple angle property. Like what was that? Vertical opposite angles in two lines, two intersecting lines, that is 30 degree. This line and this line. Okay, so 30 degree we have. So this I naught again, what will be this I naught theta? Let's say theta again, what we can do, tan inverse of IW by IM. We can get theta because I naught is made of that, and that will be tan inverse of, so what is the, so magnetizing current component is 10 ampere and loss is 6 ampere. So this will be 10 by 6. Okay, I'll just see what is the value of that. Oh sorry, this will be 6. Winding loss component is 6 ampere, no? Sorry. So this is 6, this is 10. This is magnetizing current. So this will be again, this will be 0.6, this will be 31 degree approx. So this we have equals to 31 degree. We know this is 30 degree, we know this is 31. So what will be this? 90 minus 30 minus 31. Simple mathematics. So this angle, full angle will be, it will be 90 minus 30 minus 31. It will be equal to 29 degree. So this we all are doing just we because we want to calculate IP. Based on that only we can get this phase angle error. So phase angle error, I will tell you what does that mean. So we have 29 degree here. Now we have the angle between two phasors. So we can calculate IP from there. But since they are talking about the phase angle error, so phase angle error is the angle between this primary side secondary current, that is IS by A, and between the primary current, this, let's say delta it is, or delta you can say, and this was I naught. Okay, so this we know, this is the phase angle error. So this is the like normal terminology which they use for phase angle error in instrument transformers. So this is the angle between IP and IS by A. So we have to calculate this delta. We know this whole thing, that is theta. That is, sorry, alga, this one. This, the angle that is 29 degree we got. So this whole angle is 29 degrees. So what will be delta? So in order to calculate the angle between this like the resultant vector and this base vector, that is simple, like if you know your vector calculations. So this let's say I denote this as alpha, I will denote. So this alpha is equals to what? It is tan inverse. So nothing you have to remember, it's just simple vector calculation. Is by A sine 29, that is the full angle between them. So we'll get this angle alpha divided by I naught plus Is by A cos 29. So basically we are taking the tan of like we are taking this as a reference, and then we are calculating tan of this alpha angle. Okay, it's just simple trigonometry, nothing else. So we know Is, we know A, we know I naught. Okay, and Is is basically the actual rated, this 5 amperes, that is the rated current of the secondary, that is 5 amperes, you know. One so A we know, that is, or 1 by A we can say, 1 by A is what, 1000 by 5, given in this is the 1 by, this is the reciprocal of the transformation ratio, that is 1 by A. We know everything. So alpha will be what? Based on this alpha we will calculate that as 28.67 degrees. Now what will be the phase angle error? Phase angle error is delta, as we discussed here, delta. So delta will be what? This 29 angle full angle minus this alpha, it will be 0.324 degree. So this much phase angle error has been introduced because of this the burden at the secondary side, that is this angle 30 degree, and also because of this loss component I naught. Okay, earlier we discussed how this ratio error was introduced. It was because of this burden, sorry, not for because of the burden, because of this the loss and the magnetizing current component of I naught or I naught. And now we saw that the phase angle error is being introduced because of this 30 degree shift in the secondary side of this transformer, secondary side current, and the this loss component as the magnetizing current at the primary side. Okay, so this phasor is very important. You should have this idea, and it's very simple also. Now I think you know. So this is the equivalent circuit of any transformer. So if you have this thing in your mind, you can calculate based on the phasor. So this is done. So now we have time. So now done with this PT and CT. So let's go for like more fun part of that, this flip-flops and all. So we will see some interesting questions on flip-flops and digital circuits that I think you will also enjoy while solving this. So yeah, we'll start with this first question. So D latch, T flip flops, you read in your lectures, and then toggle this SR flip flops you have read, then counters you have read. So these questions will be just based on that. So, and these will be simple only, digital, yeah. So the question says that consider the D latch shown in the figure. So this is we have D latch, which is transparent when its clock input CK is high. Okay, and has zero propagation delay. So they are saying it is having like whatever it is giving, it is just outputting at the same time, no delay is there. And in the figure, the clock signal CLK1 has a 50% duty cycle. So CLK1, so this clock cycle is having like 50% on, 50% off. That what does this mean? And CLK2 is a 1/5 period delayed version of CLK1. So CLK2 we are giving by delaying it by 1/5 of the CLK1 clock. Okay. So now they are saying the duty cycle at the output latch in percentage is. So whatever we are getting at the output, what will be the duty cycle of that output? So just think. Now it's digital, so it will be little easy for you. So I'll not draw it again here. I'll just draw output here. Okay. Mm. So, so if we talk about the output, so output will be when the clock is active, then only this will work. This thing will work. And second thing, this clock when clock 2 is active, then it will be active, and clock 1 only, then only it will give output 1. So if we have clock 1 as the high, then only it will hold that, and then it will give that as output. So we have 1 here, we have 1 in this region, we have 0, we have 1 in this region, we have 0, 1 in this region, we have 0 here, 1 1 0 0, sorry, 1 0 here, 0 here, 1 0, like this. So what will be the output? So simple, when clock is active and this is 1, then only output will be 1. So in this region, in this first region, this is 0, so clock is inactive. Clock to the this signal is inactive, so we will not have any output. Then we have both 1 here, 1 here, 1 here, so this is also active, this is also 1, we will get 1 here. Then in this region, this is 0, the clock 1, this the input to that D latch is 0, so that we will have 0 here. Okay, and then we have 0 0, the both are 0, so we will have 0 here. Then again this is 0, so this will be 0. Then again we'll have 1, then for this region it will be 0, and similarly so on. So what will be this time period? So we are talking about this is T, full T, and how for duty cycle is basically how for how much time that system was in high state. So duty cycle for the resultant output will be Q will be T on by T off. So it will be what it will, this will be what, so we have this much is T by 2. So this is half clock cycle, because they said this is 50% duty cycle. And if you talk about only this will be what, T by 2 minus T by 5, because we just subtracted this thing from this thing. Simple maths. Divided by T. So this we will get as 3 by 10.3, that is 30% duty cycle we will get at the output. So this is at 30% duty cycle. Okay, easy. So this only like flip-flop questions will be like this. It can be difficult like this. So yeah, just read the question. So now we have this unequal propagation delay concept. We will not go in detail for that. We'll just use that thing for this. So this is again a NAND gate based latch circuit. So it is having non-zero delay. The present input conditions P equals to Q equals to 0. They have given that these are the initial conditions of this. If the input condition is changed simultaneously to P Q equals to 1, so now they are changing this from 0 0 to P equals to Q equals to 1, then the output X and Y will be. So we'll have to do one assumption here. Let's TPD. So this is, let's say, 1, this is 2. So the propagation delay of 1 is less than TPD of 2. Okay, so this is one thing. We are just assuming, we can assume other way also. I think that will not be an issue. So we just assume the propagation delay of the first, this one, is less than the propagation delay of the second NAND gate. Now the the question says that we have py and x1. So x1 basically is the next stage of this x, and we know we have y1, the next stage of y. Okay, so initially it was 0 0. They're saying it was 0, this was 0, then it is changed to 1. Okay, we will say. Now they haven't mentioned about this x state. We will just assume it to be 0. Okay, this is 0, just let's say 0. Okay, I didn't mention the options, but anyway, we'll get to the answer. So this was let, this is also let. You can go for 1 also, 0 also. Okay, no issues. So this is x1, let's say this was 0. Now if this is 0, this is 0, so this was 0, so this 0 came here. We, oh sorry, this was p, oh this was q. Okay, this was q. Oh, okay. Sorry, this is y only. Mm, this, remove this. We let's say we will let this as, we will assume this y to be 0 initially. It will not matter if you are assuming x1 as 0 or y as this is y1, let's, or just remove y1. So now again, yeah, so we have initial condition of p as 0. Okay, then we have let's say we assume this, the initial condition of y as 0. Now we change the state of p to 1. We will come to q now. So now what will happen, if it was 0, this was 0, so this 0 will come here. We had we change this to 1. So this is what, this is a NAND gate. So this will be AB, then bar, this is AB bar. So 1 into 0, it will be 0, we will get this as 1. So this will be 1 here. Okay, now, and now the second step is what, q. If we talk about q, and q, from 0 it has become 1, so this is also 1 now. Okay, this is also 1, so from 0 to it has changed to 1. So this is 1, we have 1 here, we got 1, so this 1 will come here, 1, and we have 1 here. So 1 into 1, it will be 1, but ultimately this is a NAND gate, this will be 0, y will be 0 only. So x1 was 1, it became 1, then y1 will be 0. Okay, so what we observed, so the output became 1 for x and y1 becomes 0 when we changed the state of p and q from 0 to 1. Okay, and if we would have done this other way around, like let's say we would have observed this as 1 for the initial condition, then from this state was now x1 was 0, y1 was 0. When we converted p from 1 1, from 0 to 1, 0 to 1, if we would have taken this 1, then it would have been again 0 to 1. We have changed the state from of p and q, then x1 would be sorry, this was 1, so x1 would have been 0 and y1 would have been 1 in that case, if we would have changed this initial condition of this y. Okay, so ultimately the answer, so I forget to give you the options in this question, so that's why like you're saying where this question is going, the answer of this question is going. But anyway, the answer will be the conclusion will be, if we change the state of P and Q to 1 and 1, then X will become 1 and Y will become 0, or X will become 0 and Y will become 1, or basically X and Y will change their state. Okay, like this. So but if you would have seen the options, then it would have made more sense. But anyway, so you got the things what we have to do when we have some initial conditions. We will have to assume something if we have not given these like all the things in digital flip-flops and all those. So this is okay. Then yeah, this question, yeah, so just read this question. We have to calculate ultimately the average power dissipated in this resistor R. So basically in this question I will give you, in next class I will give tell you the options also, so that like it will become the full question, then it will make more sense. Yeah. So now, but this question, assume that all the digital gates in the circuit shown in figure are ideal. Okay, the resistor R equals to 10 kilo ohms and the supply voltage is 5 volts. We have these D flip-flops are initialized with logic values 0 1 0 1 and 0 respectively, so they are initialized. The clock has a 30% duty cycle. So now we have to calculate the average power dissipated in resistor R, and add one page in there. So just read the question. So this will be the last question maybe for today. We have done too much today. So for understanding D1, D2, D3, D4, D5, initial states are uh, 0 1 0, 0 1, 0 1, then 0, and we have this, let's say this will be Y. Okay, this Y is what this is a OR gate. Okay, so this is a OR gate, so and it is getting this Q3 as its input and Q5 as its input. So this is equals to Q3 plus Q5. That is the expression for OR gate. Can I minimize? No. Okay, so yeah, this is Y output. We have this Y output. So initial, and this is based on Q3 and Q5, and D1 value is based on D5 value, Q5, let's say Q5, because this Q is being given a feedback to this D1, and this is a Q5, so this is based on, so the D1's next stage will be Q5 and D2 next stage will be depending on Q1, so this is based on Q1, this is based on again Q2, this is on Q3, then this is on Q4. Okay, so this is basically acting as a shift. So for the next step, the 0 will be here, this will be here, this will become, so it will shift like with 1 bit like this. Okay, for next step what will happen, again this will be here 1, this will be 0 0, then 1 1. Okay, oh, this is 0, sorry, this will be 0 for the next step. So they are saying so they are saying for like 30% duty cycle what will be the power dissipated. So we are just we have to see when this Y output start repeating itself, so we will go only till that point value. So for first, let's say for first case, what will be Y? It is Q3 plus Q5. Q3, yeah, so Q3, okay, I will have to, so Q3 is basically this D3 output and Q5 is this output, D5 output. So this will be 0 initially, 0 plus 0. For the next stage it will be 1 plus 1, it will be 1. For the next stage it will be 0 plus 0. Okay, for the next stage again we are shifting, first value comes here, then 1 0 0 1, these two values it will be 1. then again we shifted, this will be 1, first this value here, then 0 1 0 0. These two will values or operation of I, it will be 1. Then again shifting happens, then this will be 0, then again 0 1 0 1, this will be 1. So we have to stop when the pattern starts repeating. Let's see. So this was unique, 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 unique. Here 0 and 1. We are getting 0 and 1 here also. Let's see if next is 1. We'll see. So this will be 1 0 0 1 0. So this will be what, 0. So again this becomes 0. So again this is repeating. Let's see if that the next is 1 0 1 0 0 1. So this will be 1. So that means it is repeating now. So till this point it is fine, after that it is repeating. So we have this as a unique output for this cycle. That means we have 0 first, then we have 1, then we have 0, then we have 1, then we have again 1, then it is repeating. So till this point we have this is 1 1 1 0 0. Now what is the power? So ultimately we have to calculate the power. So power will be, that is this output, and logic, and 1 means level high, and that will be like the high voltage, the 5 volt that is being given in this supply volt, given in the question, supply voltage. So what will be the power? The voltage across this, V square by R. Okay, and that voltage, whenever this will be 1, that means it will be 5. Okay, so this will be 5 square by 10k. But we are talking about, they are saying, they are asking us to calculate the average power. So this should be average. For average, it will be multiplied by the by the time where this was high, this output was high. For all the uh, time it was not high, the output was not high. So for which particular state this output was high, so that will be T high divided by the total T total. Okay, and what will be T high? T high we are getting for 3 times, 1 1 1, 3 times, for total of 5 states. 1 stage, 2 stage, 3 stage, 4 stage, and 5 stage. 1 2 3 4 5. So total T clock is 5, and high stage is 3 out of 5. So we will get 3 by 5 here. So we will get this as 1.5 milliwatt P average. Okay. Yeah. So this was the question. So I have like more interesting questions, like mod of this, and then the output of this. Like we have to calculate that based on default flip-flops. Then toggle flip-flop questions are there, and then have some interconnection toggle flip-flops. All are interesting. So it is. So this three will do in next class. Yeah. So yeah, that's all for today. So if you have any doubts in any of the today's lecture part, then you can tell me. Otherwise, yeah, thank you. So if you don't have any doubts, then yeah, so we can end this session today. So thank you for participating, and yeah, we'll meet next week this same time, Tuesday 6 to 8, and I'll post this recording also in the YouTube. So thank you for participating. So I will end this call. Yeah, thank you.